Okay, I'm going to make a start, everyone. Good morning. Today we have acids and bases. So today's lecture, I think, is going to be a little bit content-wise more easy to sort of reach and grab hold of. I just want to make a few comments briefly about the midterm. I already posted some comments on that. I'm pretty happy with the results. I think it could have been a little bit better. The pass average is 6.5. It's okay. You know, the distribution of grades is pretty Gaussian, which is good. Of course, there's some people, I think, that didn't make it. And my advice to those is just, well, first of all, not to panic, because that's not going to help. Secondly, to realize this midterm is only 35% of the overall grade, right, which is, you know, we still have a participation grade and we have a final, which counts 45%. So it's still possible to sort of salvage the situation, but it's going to require, you know, really pulling out the stops and studying like crazy. Another thing is, I mean, nobody like contacted nor me or Fabrice or Marie for help, you know. So again, I made it very clear at the beginning of the course, if you're really stuck with something, please don't hesitate to contact us. And I didn't receive any emails, and nor did my colleagues, so we thought everything was okay. All right, so I think just, you know, make use of that. If you don't understand something, that's what we're here for. We're here to help. Anyway, so I think just for those that didn't make it, it's not a total train smash. Just really pull out the stops for the final. You have all the materials at your disposal. Make use of them, and we'll go through the midterm this Thursday, so you can see where you fell down. Okay. So today's all about acids and bases. Very important. Very important, not just in chemistry, but also in biology, geology, and all the other disciplines that sort of connect to chemistry. Very important, understanding something about this. And I'd like to start off with a bit of history about acids and bases. It's always nice to see where it all came from. So this whole story started about 2800 BC, so really a long time ago, when people discovered that you can take ash and mix it with animal fat and make some sort of a soap, right? And these ancient people noticed that this has some sort of property that removes various dirts, and so that's where this whole thing started. And the name actually is Arabic. Alkali is an Arabic word derived from this word here, which refers to the ashes of a plant, which when burned makes basically soda ash, which is what they used to make soaps originally. So the name alkali is actually derived from Arabic. And alkali actually, the word alkali refers to the hydroxides, soluble hydroxides of group 1 and group 2 metals. So the alkaline, the alkali earth metals, that's why they're called the alkaline and the alkaline earth metals, right? So these make hydroxides, and we call those alkalis, and they're of course basic. And here are a couple of examples: sodium hydroxide, potassium, magnesium hydroxide. An important point worth considering is that all alkalis are bases, but not all bases are alkalis. We'll see that in a minute. All right. So that's the story for bases, or at least for alkalis. Acids come from the Latin word acidus, which means sour, okay? And yeah, basically just a bit of interesting trivia. You know, a lot of people think that Bacon was the one that started the scientific, or Descartes really started the scientific method, but actually if one looks at history, this guy over here is sort of considered at least the father of chemistry, right? Already in the late 8th century, introduced scientific and experimental approach to alchemy. So it's very interesting if one looks at the history of science, that it really goes back further than one thinks. Anyway, so this whole business of acids really also comes a little bit from alchemy. This is when people were trying to convert you know, base metals into gold. They didn't really understand basic chemistry. Of course, they didn't know at that stage the notion of the nucleus and atomic number and so on. They were trying to convert iron into gold, and one of the things that they're trying to do was to dissolve it up in acids and stuff like that. So this is sort of the starting point, at least, of acids, right? So acids, of course, all around us. I mean, here are some examples. Every time you bite into an orange, you know, you taste citric acid. Apples have malic acid, lactic acid in milk, and if anyone's ever been sort of bitten by an ant, it really burns because they release formic acid, right, which stings. These are actually the chemical structures of some of these acids. These are ball and stick models. This is what they look like. And you can see, very interesting in the case of these are organic acids. You see they contain these carboxylate groups here. They tend to be chiral, meaning they have centers that are asymmetric. So that's, for example, a chiral center, that's a chiral center, and so on. Right, so you talk about different stereoisomers of lactic, malic, and citric acid. So acids, of course, all around us. We've encountered them. Bases as well. We use them to cook. We use them to clean. Particularly cleaning agents tend to be bases. Here are some examples. Okay. Soap tends to be basic too. Yeah. So these are just some examples of everyday acids and bases that we've all encountered. This is a pH scale with some sort of, let's say, common everyday substances, and you can see we're going to get into detail a little bit later on about how this pH scale actually works, but 7 is considered neutral, and that would be the pH of pure water. If we go to the acidic side, you'll see milk is slightly acidic, bananas, tomatoes, grapes, and then at a pH of about 2 you have a lemon. Gastric juice, which you see here, this is the stomach. Gastric juice has a pH of about 1, right? Because there's HCl in your stomach, which helps with digestion. And if we go to the basic side, you see eggs are slightly basic, baking soda, ammonia, bleach, and so on. So this is interesting because these are really compounds and substances that we encounter every day. And you can see in our house, we all have these substances, basically, and they have really a broad range of pHs, from 2 right through to 14. So acids tend to be sour. They tend to react with metals to produce hydrogen. They dissolve carbonate salts, releasing carbon dioxide, so they react, some of them, to produce carbon dioxide and turn blue litmus red. And bases tend to be bitter, they tend to be slippery. That's why soap is slippery, because it's basic. They react with acids to form salts. You have a typical acid-base reaction to form a salt and water. It's a so-called neutralization reaction, and it turns red litmus blue. Right? So these are just some basic properties of acids and bases that we've all sort of encountered. So what I'd like to now start doing is sort of get stuck into the different models of acids and bases. That's sort of a basic introduction. I think if one looks at acids and bases, there's really 3 important theories. The first one comes from a guy called Arrhenius, a Swedish chemist, and he actually won the Nobel Prize in 1903 for his work on electrolytic dissociation. Now this guy, very interesting, a bit of trivia, was really the first one to sort of uncover the greenhouse effect, right? He was the one that did experiments linking carbon dioxide to increase in temperatures. So it started with Arrhenius. But what he also did was he came up with a very interesting theory for acids and bases. And what he basically said, in a nutshell, is an acid is a source of protons or H pluses, and a base is a source of OH minuses. That's the Arrhenius model, okay? So this is a neutralization reaction. I was mentioning this earlier. You can see an acid plus a base forms a salt plus water. And according to the Arrhenius model, if you take HCl and you dissolve it in water, you form H pluses and Cl minuses. It dissociates. So it's a source of H pluses, so it's an acid. Sodium hydroxide, which is an alkali, which is a base, remember, alkali bases. If you take sodium hydroxide and you dissolve it in water, you get Na plus and OH minus. It's a source of OHs, or OH minuses, hydroxide ions. So according to Arrhenius, that's a base. And if you mix the two, you get you get a neutralization reaction. So this is what I've just said here, right? HCl is a source of H pluses, NaOH is a source of OH minuses. So according to Arrhenius, the one's an acid and the other one is a base. And you can actually represent this equation at the top here, which we call the sort of full molecular equation. You can represent in ionic form as well, like this. And basically, that's another way of writing down the equation. Because remember, these reactions are taking place in aqueous solution. That's why we have these subscripts here. Okay, so this over here at the bottom we call sort of the net reaction. And this is what happens if you react an H plus with an OH minus. They sort of see each other and they neutralize each other. The take-home message is Arrhenius's theory is simply in terms of how we define an acid and a base. Okay? Now, the problem with the Arrhenius theory is that it doesn't account for bases that do not contain OH minuses. In other words, it only accounts for alkalis, right? Remember we said alkalis are group 2, group 1 or group 2 soluble hydroxides. But I mean, there's many other substances that are basic. So the Arrhenius model breaks down if you have non-OH minus ions. For example, ammonia is a base, but it doesn't have OH minus. So when you dissolve ammonia, it doesn't dissociate like NaOH. So the model breaks down. And another place that it breaks down, it doesn't account for the role of the solvents in the ionization of a solute, right? So there seems to be a solvent effects as well. So we need a new model, a better model. And so there is a better model, and that's Bronsted-Lowry, okay? And these guys worked independently on acids and bases, and more or less at the same time actually came up with the so-called Lowry-Bronsted model of acids and bases. And they sort of refined the Arrhenius model somewhat by saying, okay, an acid is a proton donor, and a base is a proton acceptor. So that's now the Bronsted-Lowry model. Arrhenius is an acid produces H pluses, a base produces OH minuses, and they simply say an acid is a proton donor and a base is a proton acceptor. And in the context of Bronsted-Lowry, we have we talk about acid-base conjugate pairs. We have typically an acid and a base, right, which forms a conjugate base and a conjugate acid. Okay, so things always sort of go hand in hand. We'll see an example here at the bottom. This over here is actually acetic acid, which you find in vinegar. And if you take acetic acid and you dissolve it in water, you actually have a sort of an acid-base equilibrium. That's why I use a double arrow. What actually happens is this guy here, if you look at, as we go from left to right, this guy gives its proton to the water to form H3O plus, and we're left with this guy here, which is CH3COO minus, the acetate ion. So is this guy behaving as an acid or a base? Acid, yes, because it's a proton donor. And what's the water behaving as? Base. Right, that's going left to right. If we go right to left, what's happening if we go the other way? What's this guy doing?
Accepting H plus.
Right, it's picking up a proton, so it's behaving as a Lowry-Bronsted base, and the H3O plus is behaving as a Lowry-Bronsted acid. It's a proton donor. So that's very simply how this works. This is an acid, this is a base. This would be the conjugate base of this acid, and this would be the conjugate acid of this base. So you talk about acid-base conjugate pairs, right? Okay. So that's basically what I've just said. You have the acid and the, so here you've got the, well here's, sorry, this is another example. Here we have basically water, just simple water can behave as an acid and or a base. It's a so-called amphoteric substance, meaning that it has the capacity to both accept and donate a proton. We call that amphoteric, okay? So you can see in this case the water molecule, basically this water molecule can donate a proton to this guy here. You form OH minus and H3O plus, and if you go in the other direction, it happens the other way around. So this would be this guy would be behaving as an acid. This is a base. This would be the conjugate base of this acid, and this would be the conjugate acid of this base. So that's how it works, acid-base conjugate pairs. Okay, and here you have just two more examples. Here you have water reacting with HCl, right? You form H3O plus and Cl minus. What's happening? The HCl is acting as a proton donor, right? It's donating its proton to H2O to form H3O plus. So that, guys, the conjugate acid of that base, and that's the conjugate base of that acid. So the conjugate base is what you basically have left after the proton donation has taken place. Okay. And the last example is ammonia, right? So I said earlier, you know, the reason why we needed the Lowry-Bronsted model was because there are bases like ammonia which don't produce OH minuses, and here you can actually see that it kind of does produce an OH minus in a way, but not from the NH3. The OH minus comes from the water. So the NH3 in this case, plucks a proton from the water molecule, and you form OH minus and NH4 plus. So again, you have the conjugate acid-base pairs. So this is basically what's happening in that reaction schematically with ball and stick models, right? We have ammonia, NH3. We all know that it's trigonal pyramidal, right? Because of VSEPR theory. That's why we can rationalize that it looks that way. And you can see that it basically, what it does is, it basically, this water molecule here donates, it's behaving as an acid, donates its proton to the ammonia to form NH4 plus and OH minus. Actually, those two would associate to form ammonium hydroxide. And so you can here very nicely again see the acid-base conjugate pairs left and right. And these are typically equilibrium reactions, right? So that's why we use this arrow. Are there any questions? Okay. It's quite straightforward. Now, we've learned about K, the equilibrium constant. And we know that the equilibrium constant is basically the concentration of products over the concentration of reactants, right? Essentially. Right, you've got to, of course, remember to take the stoichiometric coefficients into consideration, products over reactants. Now, it's very useful to talk about the equilibrium constants for acids and bases as well, because it will give us a measure of how strong or weak an acid or a base is. Okay? But when we talk about the equilibrium constants for acids and bases, we neglect the water. Why would we just neglect the water? So let's say I take ammonia and I dissolve it in water, and I want an equilibrium. So this reaction here. If I want to write an equilibrium constants expression for that, right, what would it be? Just K, Kc. Well, it would be the concentration of the NH4 plus times the concentration of OH minus divided by the concentration of NH3 times the concentration of OH, wouldn't it? That would be the Kc expression for that. The equilibrium constant. Let's write it down. Now, we can actually just drop the water altogether in this case, because the water is actually a solvent. It's not really a reactant. This is the solvent. So what we typically do is we talk about a so-called Kb, a base ionization constant, which is essentially the same as Kc, the expression we just dropped the water. Okay? So we call that Kb. So this would be the so-called base ionization constant for ammonia. This is the expression. Now that's K subscript B, right, for base ionization constant. And we have, in general, that Kb is the concentration of the conjugate base times the concentration of the conjugate acid over the concentration of the base, like we just see in this example. Basically, the take-home message is it's like Kc, you just drop the water because it's behaving as a solvent. Now, we can do the same thing for acids. So here we have now an example of a generic acid called HA. Don't worry about it, could be HCl, could be HI, doesn't really matter, some acid. And this is now, again, this dissociation reaction. The acid dissolves in water to form this guy here, H3O plus A minus. And here are the acid-base conjugate pairs according to Laurie-Bronsted. Now again, I can write a Kc expression for this reaction, which would look something like that. But we can also talk about a Ka value, right? An acid ionization constant, which is nothing more than the K expression, or that should be Kc, and I've just neglected the water. Why have I neglected the water? Because it's the solvent. It doesn't tell us anything. That's why in the Ka and the Kb expression, it's like Kc, except we just drop the water. And that tells us something about the degree of ionization. Okay? So these are two important new types of K, Ka and Kb.